Today we are going to start the new topic, that is applications of Gauss law. So in the previous video we have discussed the meaning of electric flux and the Gauss law, right? So what was Gauss law? We know that when we consider a closed surface and that closed surface is placed in a uniform electric field, then according to the Gauss law the total electric flux will be equal to charge enclosed by the closed surface divided by epsilon naught. So this was the statement given by Gauss law. So now we are going to apply this Gauss law in the calculation of electric field due to different types of charge distribution. So already we have discussed the different types of charge distribution. The first type of charge distribution was the linear charge distribution. Then we have the surface charge distribution, and then we have the volume charge distribution. So first we are going to discuss the electric field due to the infinite long straight charged wire. That means there will be a long wire which is having charges, positive charges, and we are going to calculate the electric field. Clear? So we are going to calculate the electric field at any point due to this charged wire. So before applying the Gauss law, what are the important steps that we need to remember? So the first step, in order to apply the Gauss law, we have to consider the Gaussian surface, right? So here you can see that we have taken the charged wire of uniform charge distribution and we have taken the Gaussian surface. So this Gaussian surface is a cylindrical in shape. Here you can see that this is our Gaussian surface, right? So why the shape is cylindrical? Because if you see the charged wire, the charges are all point charges and it is distributed uniformly, and you know that for a single point charge the Gaussian surface will be spherical. Now if we draw the spherical shape, then one after another we have to draw the sphere, and you know that if we go on drawing circle over circle, then the shape will come out will be a cylinder. So the Gaussian surface, the shape of the Gaussian surface will be a cylindrical Gaussian surface. Now there are how many surface? You can see that there is, this is the first surface, the bottom surface, 2, and third surface, right? So there are two surface that is present at the top and the bottom part, and there is a curved surface. So we are going to calculate the electric flux because of all the three surfaces. So how to calculate the electric flux? We have considered the Gaussian surface. Now we are going to calculate the electric flux, right? So before calculating the electric flux, what you have to do now? Can you tell me? First step is to consider the very small elemental area, right? And we have to check the direction of electric field vector and the area vector. So here you can see for the top surface, this particular surface, the direction of area vector is perpendicular to the electric field, because if you see the diagram, this is the direction of electric field and area vector is perpendicular. That means what will be the angle? The angle will come out 90. And similarly at the bottom part also, this part, the area vector is perpendicular to the direction of electric field. So here also the angle will come out how much? 90. So for these two surfaces the flux will be how much? The flux is given by EA cos 90, and cos 90, I think all of you know the value of cos 90 is how much? 0. So for the top surface and the bottom surface the electric flux will come out 0. So only we are going to calculate the electric flux for this particular surface, that is the curved surface. So let us try to calculate the electric flux for the curved surface, right? So for the curved surface, how we are going to calculate the electric flux? So for that reason, we have to consider a very small elemental area, right? So here you can see that we have considered this very small elemental area of ds, and the direction of this small area vector is along the direction of the electric field. Here you can see that both the electric field and the area vector ds are in the same direction, so angle between them will be how much? 0. So we can find out the flux. The very small flux will be how much? Integration E vector dot ds vector, right? So this is the electric flux. If we calculate the flux for the whole curved surface, then we have to do the integration. So by using the integration, we can calculate the total flux. Now, since electric field is uniform everywhere, so we can take it outside of the integration, and within the integration only ds will be left, right? And in the right hand side, we will be getting the net flux. So this will be the net flux. Now, can anyone tell me what is the area of this curved surface? Now, from maths, you have got the area of the curved surface of the cylinder. So that is given by how much? 2 pi r multiplied by length of the cylinder, right? So what is the length of the cylinder? L. So here the curved surface area is given by twice pi r multiplied by L. So here what we have to write now? So electric field E multiplied by 2 pi r L. So this will be equal to how much? The net flux. So I think this much all of you have understood. So this is the total flux due to the curved surface of the cylinder. So that is given by E multiplied by twice pi RL. Now in order to apply the Gauss law, so what you have to do now? So now we can say that using the Gauss law, so using the Gauss law, what we know that the net flux, this already we have discussed in the previous video, that net flux is how much? Total charge divided by epsilon naught. So how much we have got? The total flux E multiplied by 2 pi RL, and this charge can we write like this, lambda into L. So I think all of you know lambda was the linear charge density, and since here the charge distribution is one dimensional, so we can consider lambda. So what was lambda? So lambda, I think all of you know, lambda was given by charge per unit length. This was the formula of lambda, right? So from here charge will be how much? If we do the cross multiplication, you will be getting lambda multiplied by L. So by further calculation, how much you'll be getting? So if we do the further calculation, so then it will be coming out. So therefore if we do the further calculation, then E will be how much? So this will be lambda L. If we do the cross multiplication, then it will be 2 pi r L into epsilon naught. So from here you can see the result, so that it will be 2 pi epsilon naught r. So this is the expression for electric field, right? So this is a very important expression, and this derivation is also very much important for your exam. This normally comes for 3 marks question. So you have to calculate the electric field due to the charged wire. Since the charged wire is one dimensional, so we have considered lambda. So what is lambda? Lambda is charge per unit length. So the final result will be electric field due to the charged wire is given by lambda by 2 pi epsilon naught r. So here you can see one thing, that the electric field, it is inversely proportional to the radius. So what is r? R is the radius of the cylindrical surface, and as r increases, the electric field will decrease. Okay, so I think you have understood this derivation. So let us move to the next derivation. So our next derivation will be, so now we are going to see the next derivation. So the next derivation will be electric field due to infinite charged plane sheet. So there will be a plane sheet in which the charges will be distributed uniformly. So what is the charge distribution we'll be using on the sheet? So here you can see that this is the sheet in which all the charges are distributed uniformly. The red color dots represent the charge distribution. So the charge distribution, since there we can see that there are two dimension only, right? So since there is length and breadth, and so we can consider the charge density to be sigma, right? So what was sigma? Sigma was the charge per unit area. So here you can see in the picture that the charges are distributed uniformly over the area. So we can consider the charge density to be sigma. So what was sigma? Sigma was charge per unit area. So now which type of Gaussian surface we can consider here? So here also we can take the example of the cylinder. Why we can take the cylinder? Because you can see that if we take the cylindrical Gaussian surface, then it will enclose all the charges, right? So here all the charges will be enclosed by the cylindrical Gaussian surface. So here we can get the electric flux for this point, and also for this point and this point. So let us try to calculate the electric flux for all these 4 points. So let us calculate one by one all the electric flux. Now here for this point you can see that the electric field direction, since these are positive charges, the electric field will be like this, right? Outward, and area vector is perpendicular, so the angle is 90, right? Same here also, electric field is like this, angle will come out 90. And for this part the direction is same, electric field and the area vector. And here also you can see that electric field and area vector both are in the same direction. So which flux will get cancelled out? So this electric flux will get cancelled out, and this one. Why? Because the angle is 90 and flux will be how much? 0. So only we are going to get the electric flux for this surface and for this particular surface. So what will be the total flux? So if we write the net flux now, so what will be our net flux? So the net flux is given by, you can see here, the net flux is given by E vector dot A vector plus E vector dot A vector. Why we have put it in two times? Because only we are getting the flux for the two surface, one for the outward surface of the cylinder and other for the left outward surface of the cylinder. But the rest of the curved surface, the electric flux will become 0. Why? Because the angle between electric field and area was 90. So how much will be getting now? So 2 times E dot E. And what was the angle between E and A? So that was 0 degree, right? So here EA we can say cos 0. So how much will be getting? 2 times E dot E. Now from here we can say that, so from here we can say that using the Gauss law, now we can apply the Gauss law, right? So by application of Gauss law, so the net flux was how much? That is given by charge upon epsilon naught. So how much we have got the net flux this time? So 2 times E dot A, and charge we can write as sigma into E, right? So what was sigma? So sigma was charge per unit area. Since it is a two-dimensional charge distribution, so the density will be sigma, that is represented by charge per unit area. So if we do the simple cross multiplication, you will be getting sigma into A. So after solving this equation, how much you will be getting? So after solving this particular equation, you will be getting that electric field E will come out sigma by 2 epsilon naught. You can check the result by yourself. So the electric field due to the infinite charged plane sheet is given by sigma divided by 2 times epsilon naught. So this is the calculation of the electric field. This derivation is also very important. So this is the second application of Gauss law. Now let us move to the third application of Gauss law. So the third application we are going to take is spherical shell, right? So we are going to calculate the electric field due to spherical charged shell. So there will be three different positions where we are going to calculate the electric field. The first position will be outside the shell. So for the position outside the shell, the you can see the point. So here you can see that this particular point is point P is outside the spherical shell, right? And for a spherical shell, how the charges will be distributed? So all the charges will be distributed over the surface. So why the charges are distributed over the surface? Because if you see this picture, if we provide any charge at the center, then what will happen? This charge will be present where? Now because of the mutual repulsion, since there are lots of positive charges are present, so there will be mutual repulsion, and because of this mutual repulsion, all the charges will be present on the surface. So whenever we provide any charge to a sphere, then this charge will be uniformly distributed over the surface of the conductor. This is very important. We are going to discuss properties of conductor. In that we are going to discuss this in detail. So always remember, when we provide any charge to the center of the conductor, then because of the mutual repulsion, all the charges will be uniformly distributed over the surface of the conductor. So this is the particular point which is outside the spherical shell, and here you can see that capital R is the radius of the sphere, and small r we have taken the distance from the point P to the center O. So we can say that R is very much greater than capital R, right? So we are going to calculate the electric flux at the point P. And here you can see the Gaussian surface. The Gaussian surface will also be a spherical in shape, right? So first what you have to do, first we have to consider a very small elemental area, right? So first we are going to calculate a very small elemental area. Now can you tell me what is the direction of the electric field due to the charges? So all the electric field will be directed like this, right? Radially outwards, since it is positive charge. So let us take one small elemental area. Let us take this area, so that is dA, right? And you can see the electric field vector, this one. So are the direction of electric field and area vector same or different? So from the diagram you can see that electric field is perpendicular to the Gaussian surface, and similarly dA vector is also perpendicular to the Gaussian surface. So what will be the angle between them? The angle between them will become 0 degree. Clear? So we can calculate the net flux, so that will be the integration of d phi, so that will come out integration E vector dot dA vector. So by simplification we can get electric field is constant, so it will be integration of dE. So I think this part you have cleared. Now electric field is constant, right? So electric field is constant, so we can write the expression for electric field. So here you can write K, we can write Q divided by R square, and area. So what will be the area this time? So since we have area, so electric field we can write afterwards also. So electric field we will not going to write now. Okay. So let us keep the electric field like this only, right? So this is the area. So electric field we can write outside an area. So what will be the area? So that will come out 4 pi r square. So here you can see that small r is the radius of the Gaussian surface, and what is the shape of the Gaussian surface? It is spherical, and you know the surface area of a sphere, so that was given by 4 pi r square. So we can write E multiplied by 4 pi r square. So after further calculation, how much you will be getting? So if we do the further calculation, then finally you will be getting how much? So this is the net flux, right? So phi net, so this will be coming out E into 4 pi r square. Now we can apply the Gauss law, right? So using the Gauss law, what we know that, so then net flux according to Gauss law, it will be charge divided by epsilon naught, right? So after doing the further calculation, if we put the net flux now, so net flux was E into 4 pi r square. This is equal to Q upon epsilon naught. So what will be the electric field? So electric field will be simply q by 4 pi epsilon naught r square. So have you seen this expression earlier? So this expression is similar to the electric field due to the point charge. So when the point is outside the spherical shell, then this can be assumed that the electric field is due to the charge which is present at the center of a sphere. And the expression will be similar. The expression for electric field is given by q divided by 4 pi epsilon naught r square. So this is a very important derivation, right? So this is the position that is present outside the spherical shell. Now let us try to find out the position which is present inside, or say for example the position which is present on the surface, right? So now we are going to calculate the electric field for the point which is present on the surface of the spherical shell. So for the point which is present on the surface, it will be simply the value of small r will be replaced by capital R. Why? Because you can see that if this is the spherical shell and this is the point P, then here the from the center to the point P, the distance will be how much? Capital R, that is the radius of the spherical shell. So how much will be the electric field? Again, we can think about a Gaussian surface that is spherical in nature. The radius of the Gaussian surface this time will be capital R. Then again, we can find out the electric field using the Gauss law. Then the final expression you'll be getting is 1 upon 4 pi epsilon naught q divided by capital R square. So only this time the change will be in the value of small r. It will be replaced by capital R. I think this is clear to all of you. So let us move to the third position. So the third position is very important, right? So the third position, we are going to calculate the electric field inside the spherical shell. So here we are going to calculate the electric field at a point inside the shell. So what will be the electric field? So let us take the spherical shell like this, right? So let us take the spherical shell, this one, and this was the radius capital R, and all the charges are distributed on the surface, right? So all the charges are distributed on the surface. So now we are going to consider a particular point on the inside, right? So let the point be P. Now we have to consider the Gaussian surface, right? So let the Gaussian surface be like this, right? This is the Gaussian surface. This is our Gaussian surface, right? So this is the Gaussian surface, and let the distance from the center to the point P is smaller, right? So the distance, how much we have taken? The distance we have taken is small r, right? So this is the point. Let us denote the point P. This is the point P. Okay, this is the point P, and we are going to calculate the electric field at this particular point. So here you can see small r is less than capital R. Now can you tell me what is the electric field? So as I already told you earlier, that when we provide any charge to the conductor at the center, then because of the mutual repulsion, all the charges will be present on the surface. Now since this time the point P is at inside the spherical shell, and we have considered the Gaussian surface, but you see that the charge present in the Gaussian surface is how much? Here, can you see any charge? No. So there is no charge present inside the Gaussian surface. So I think this point is very much clear to all of you. In the diagram, you can see that there is no charge present inside the Gaussian surface. So according to the Gauss law, what we can write? So according to the Gauss law, we can write that using Gauss law, the total flux phi net is how much? Charge upon epsilon naught, right? And phi is how much? That is given by E dot dA, and that is equal to charge upon epsilon naught, right? So this is according to the Gauss law. Now in this case, what we are getting, that there is no charge, that means electric field into, we can say, the area, so that is 4 pi r square equal to 0 upon epsilon naught. Why it is 0? Because no charge present inside the Gaussian surface. So there is no charge present inside the Gaussian surface. So what will be the final result? The final result will be electric field is equal to 0. So this will be the expression for electric field at a point inside the spherical shell. I think this point is very much clear to all of you. Since there is no charge present inside the Gaussian surface, so the electric field will be how much? 0. Now let us try to draw a graph to represent the variation of electric field with the distance. So we have drawn the graphs like this, right? This is the electric field, say suppose, and this is our particular distance r. Now what we are getting at the inside point, the electric field is how much? 0. So it will be 0 now when the point is on the surface, right? So when r is equal to capital R, then we are getting the maximum electric field, right? And after that point, outside the surface, outside the spherical shell, what is the electric field? So that was E is inversely proportional to R square. So this time the graph shape will be like this, okay? So this is the shape of the graph between electric field and the distance. So I think it is clear to all of you. So that inside point the electric field was 0, and on the surface the electric field is maximum at r equal to capital R. And again when we go outside the spherical shell, the electric field is decreasing, and it is given by 1 upon r square. So the electric field variation will be like this. Okay. So I think today's lecture is clear to all of you. Thank you all of you.